So, as a software engineer, I'm used to a life of luxury, and I mainly work with Java. And whenever I write bad code, the garbage collector comes and cleans up my mess for me. But today, I wanted to do something different. I wanted to touch bare metal. Some of you might think that I'm going to be using this Arduino Uno card, but no. This is an 80 Mega 32. This is a microcontroller. It has no operating system, no USB ports, no HDMI ports, and only 2 kilobytes of RAM. Today we're going to build a completely standalone game console from scratch on a breadboard, write a custom physics engine in C++, and put the famous game Flappy Bird on it. How hard could it be? Okay, so before we start anything, let's talk about the components that we're going to use. Here in the background, you're going to see me wiring the components, but do not worry. We're going to be talking about the wiring in just a moment. So we're going to need the 80 Mega 32 microcontroller. This is going to be the brain in our project. We're going to need one breadboard and then one OLED I2C 1-inch display, 128 pixels by 64 pixels. And we're going to need a 116 megahertz crystal oscillator and two 22 picofarad ceramic capacitors, one 10k ohm resistor, one push button, and one small speaker. Any piezo speaker will do. One USB ISP programmer and a bunch of wires. This is all we're going to need for our wiring. And in the next section, I'm going to show you how to wire everything together. Okay, so now we're going to be talking about the wiring of the 80 Mega 32 before we go on soldering any component together. Hello everyone, Otis Dev from the future here. Just a quick disclaimer, I am not an electrical engineer, so the schematic for the wiring that you're going to see, it's not up to standard. I'm just using it because it's the easiest way I found to explain how to wire everything together. So back to the video. So I'm going to be drawing a very simplified version of the 80 Mega 32. I'm just going to keep the important stuff for us for this project. And when wiring, I like to split the wiring into two sections. The first section is going to be the life support, meaning any power that you're going to give to the chip. And the second section is going to be all about our data pins. Okay, so for the life support or the power for the chip, we're going to be using two pins. Of course, the VCC and the GND. VCC, it's basically the plus 5 volts that we're going to be supplying to the chip, and the GND, it's the ground. We're also going to be plugging in a Crystal Oscillator, and FYI, the 80 Mega already has a internal crystal. It runs at 8 megahertz, but we're going to be wiring our own Crystal Oscillator to overclock the chip to 16 megahertz, so we can squeeze most performance out of it. And this Crystal Oscillator is going to be plugged in these two pins, usually called XTAL1 and XTAL2. Of course, we're going to be adding some capacitors to protect this circuitry. And we're going to be using the RST pin. RST is basically the reset pin, but it's a little specific because this pin, it's what we call an active low pin. And what it means, it's basically this pin only works when it's low, meaning we give it no current when it activates. And for our case, it means that when we give it no current, basically the whole chip that just shuts down. To keep the chip working, we need to supply it a 5 volts current. And just for safety measures, I'm going to plug in also a 10K resistor here. And this is basically our life support for our chip to make it run. Now let's go to our data pins. Okay, so before we move on to our data pins, let's talk about our display and why I chose this type of display. So this is an OLED I2C display. It's a really small one. It's only 1 inch. And the reason I chose it, it's because it's really easy to use. It only has 4 pins. And if we disregard these 2 first pins, because these 2 pins are actually just for power. This is our VCC and this is our ground, and these 2 pins are our data pins. This is the SCL and this is the STA. We're going to be talking about them. This is our clock and this is our actual data pin. So for the clock, if we decide to run our game at 30 FPS, it means that this clock is going to be on and off 30 times per second. And the data pins is the actual pin where our data is going to be going into our display. The zeros and ones that are going to be turning on and off our different pixels on the display. And another reason why I chose this display is because of this I2C. This is actually the protocol used to communicate with this display. And good news, the ATmega32 already knows how to talk this protocol. It's already integrated in the chip. And it's only specific to 2 pins. The pin 22 and 23. 22 is going to be our SCL, so basically the clock. And 23 is going to be our SDA, and that's the data pin. And if you've been following at this extent, it means that the SCL pin is going to be connected to pin 22 and SDA is going to be connected to pin 23. These are 2 pins, and we have 2 last pins that are going to be used for our speaker and our button. There's nothing special about these ones. We basically can use any ones on the chip. I chose to use pin 16 and pin 17 just because they're close to each other. The pin 16 is going to be used as an input because it's going to be used for our jump button, and the pin 17 is going to be used as an output for our speaker. And this is basically all the wiring that we're going to be doing. Okay, so let's look at a real schematic of a ATmega32 chip. It's going to help us to better understand the wiring that we're going to be doing. So for the numbering of the pins on this chip, we always start on the top left on this little circle, and we go on to the other side. For the VCC and the ground, we're going to be using these two pins. And basically the same on the other side. This is the same ground, and this is analog VCC. We don't actually need to wire it, but sometimes the chip acts weirdly when it's not connected. Just to be safe, we're going to connect it also to a plus 5 volts input. And for the XTL 1 and 2, this is where we're going to plug in our crystal. This is 5 volts, and this is the ground. And for our reset pin, we're going to connect it this one. This is the reset pin. And if you noticed, the name of the pin has a stripe on top of it. This is what we were talking about earlier, the active low. Whenever you see a bar on top of the name of the pin, it means that this pin is active low. So this is it for the live support, and for our data pins, we're going to be using 16 and 17. 16 is going to be for our push button, and 17 is going to be used for our speaker. And last, we're going to be using the 22 and 23 pins. And these are the SCL and the SDA that we're going to use for our display. And this is it for our wiring. In the next chapter, we're going to be actually wiring the Atmega 32 and programming it, testing it first, then programming it. Okay, now we can start programming, but first things first, we need to prepare our development environment. So the first thing we're going to do is go to File, Preferences, and paste this link here. This is a link to a boards manager called Mighty Core. I'm going to leave it in the description down below. I'm also going to leave a link to the GitHub repo for this whole project. If you're interested in more details, you can find it there. Then we click OK. Next, we go to Tools, Boards Manager, or you can just simply click here on the left. And we're going to search for Mighty Core. This is the boards manager that we just added. And click on Install. Next thing, we're going to add a library here in the library manager. Library is called Adafruit SSD 1306, and click on Install. If it asks you for to install any dependencies, you just go ahead and agree. This is the library that we're going to use for the display, the OLED I2C display. After we install it, we basically have the environment set up, and we can start programming. But before we start actually programming on the game, I just want to display a simple message on our display, just to check that everything works correctly and that the wiring is good. Okay, so I'm going to add our libraries that we're going to need. And I'm going to use the define preprocessor. And we're gonna call the constructor for the Adafruit SSD 1306 display. Okay, great. Now, if you've ever worked with Arduino, any board of the same family, you know that all their programs have two methods, the setup method and the loop method. Basically, the setup method runs once at the beginning of the program, and the loop method, as the name suggests, it loops repeatedly and indefinitely until the program is stopped. So which means we're going to use the setup method to initialize our display, and whatever we want to display, we're going to do it on the loop method. So I initialized the display here. This method, basically, if it returns true, it means the display was correctly initialized, and we can move on with our code to the loop method. And if it returns false, well, it means that it wasn't initialized, and we go into this infinite loop and not show anything on our display. At that moment, we know that something is off. The next thing, now I'm going to show a simple message. I'm going to use the loop method. First thing we're going to do is clear our display. And this is it. It's pretty simple. First thing, we're gonna clear our display, then set the text size to 1. Next is the text color. We're using this constant from the library. It's basically to print text in white. Then set the cursor to the position 20 on the X and 20 on the Y. Then print hello from the ATmega32. Then display our message. And this will basically loop infinitely, which means after this display.display, we're going to clear our method again, set the text size, and so on. Okay, the next step now is to upload this code to our chip, the ATmega32. Okay, I've encountered a very annoying issue. So apparently Windows 11 hates this thing. This is the ATmega32 programmer that I was going to be using, but Windows 11 does not recognize it. I've tried many drivers. I've even downloaded some sketchy software and tried to rip off the driver and install a new one, but it does not work. However, we're not stopping here. If you remember that Arduino board that I threw earlier in the video, well, we're going to be using it. I'm going to use it as a programmer. I'm going to show you the wiring that I did. And in the Arduino IDE, I'm basically going to use it as a programmer and pass on the data from my PC to here to the ATmega32. Okay, so here I'm wiring the Arduino Uno to the breadboard so I can use it as an ISP programmer. If anyone is interested in doing the same thing, I'm going to leave the schematic on the screen right now. And I'm going to speed up this video. It's nothing interesting about it, so we can move on to programming. Okay, now we're back in Arduino IDE, and we need to configure Arduino Uno to make it a programmer, an ISP programmer. And to do so, luckily for us, it's pretty easy. There's an example code already available. If we go to File, Examples, and 11 Arduino ISP. Click Arduino ISP. Basically a new sketch will open up, and we need to upload all this new code to the Arduino Uno so we can make it into a programmer. Okay, to do so we're going to go to Tools, Board, Arduino AVR, and we're going to choose Arduino Uno and change the port to wherever our Arduino Uno is connected. For me it's connected on COM8, it's already chosen, and we're going to hit Upload. And this is it, done uploading. Okay, back to our test code. Now we can upload it to the chip, but actually not quite yet. We still have one last step to do. We need to set the Arduino Uno as our programmer, and to do so, first we're going to choose our board. From board, Mighty Core and 80Mega32. Second thing, our port. I'm using the COM8. And next we need to set our clock. If you remember from our schematic, we're using our own Crystal Oscillator and not the internal one. So we're using a 60 megahertz one. And we're going to choose our programmer. This is the Arduino as ISP. And one last step, we're going to burn the bootloader. And what we're doing here is basically telling the 80Mega32 to shut off the internal Crystal Oscillator that runs on 8 megahertz, and to use our own 16 megahertz Crystal Oscillator. Done burning bootloader. Ignore this message. Doesn't mean anything for us. And to upload our sketch or our code, we go to Sketch and Upload using Programmer. And we have a simple typo. And take two. And done uploading. Okay, so let's power it and test our code. I'm going to be using this MB102 power supply. They're pretty cheap, you can find them anywhere. I'm going to attach it to the breadboard and supply it with 9 volts. And make sure that the jumpers are on 5 volts also. And we can turn it on. Yes. And this is our message. If I can focus. There you go. Hello from the 80Mega32. And we can see that the text is overflowing, which is pretty good. Nice. Okay, so everything works, and now we can move on to making Flappy Bird. Okay, so let's move on to our last chapter. This is where we're going to be doing the actual programming of the game. I'm going to speed up this section a little bit. It's going to be a lot of boring code. But whenever there's something interesting or important, I'm going to stop and explain it.
2 hours later.
Okay, so let's quickly go through the final code that we're going to be uploading to the ATmega32. And of course, this code is going to be available on the GitHub repo for anyone interested. I'm going to be leaving a link down the description. So first thing, I've added the EEPROM library. We're going to be using it later to store the high score for the player. And I've defined the two pins for the button and the buzzer. I've added some global variables for the player, the obstacles, and the game state. And I've set the pin mode for the button pin and the buzzer pin, and displayed the name of the game, and added two methods, reset the game and set high score. For the set high score method, we're going to be using the EEPROM memory. And this is basically non-volatile memory, so even if we shut down our system, we still keep our high score. And we go to the loop method, where we check for the button state. And if the player pressed the button, we're going to increase the velocity by the jump strength and play a tone, and move the obstacle from the right side of the screen to the left side of the screen. Basically, it's the whole world that is moving towards the player and not the opposite. And we check if the obstacle have reached the left side of the screen. If it does, we're going to spawn a new one. We check for collision here, and finally we render our graphics, which is basically the player. It's going to be the circle, and our obstacle, the top rectangle and the bottom rectangle. Okay, so let's upload this code and test it. Great, it's done uploading, so let's test it out. Okay, moment of truth. Let's see if everything works together. Just like earlier, I'm going to be using a MB102 to supply power to the breadboard. So let's plug it in. And of course, make sure that the jumper's on 5 volts. Okay, let's go. Yes. We can't see it clearly, but it says Flappy dot, press to start. Okay, let's do that. Yes. Let's test collision. Good. Okay, so collision with obstacles work. How about the edge of the screen? It works also. And we have the message, game over, press to restart. You can see it very well because I'm using a webcam to record. But I'm going to be leaving a picture. Later I'm going to take it with my phone with the highest score I could get. I'm going to put it on the screen right now. Well, thank you everyone for watching. This was a fun project. I hope you enjoyed it as well. If anyone is interested, I'm going to leave a link to my GitHub repo for this project in the description box below. I'm going to be making more videos like this, so if you want to tune in, please do subscribe, and see you next time.